Welcome all. I am Alper Dinçer from Ankara, Turkey. I am the co-founder of a special company named Mekansal. Today I will be talking about using PostgreSQL as a NoSQL database with PostGIS to store vector data in one table. Before start, I would like to thank Steve and Crunchy Data for organizing this PostGIS Day 2020 and giving me the opportunity to talk to you. Okay, let's start with the presentation. First, let me give a little background information about myself and Mekansal. I am a civil engineer with an MS degree on JS for more than 17 years. I call myself a GeoWeb developer, loving working with spatial and location data. I was the winner of 2009 ESRI Developer Mashup Challenge, and I am the co-author of the Google Maps JavaScript API Cookbook. Mekansal was founded in 2012 and it has been working on JS and LBS projects, both for mobile and web platforms, mostly with open source software. Recently, we are also working on machine learning and deep learning projects on remote sensing data. Okay, when we come to today's topic, or let me say, story of a brand new JS web application. 2 years ago, a company asked us to develop a web-based JS application to store their feasibility analysis as reports, photos, and JS data for a nuclear power plant. We said yes and start the project, but then realized that the JS files are not structured, and even the structure for the same type of file are changing in the period of the time. Also, they don't want to ask for a change in software or database every time they upload the files. So we start thinking about how to solve this problem. We have the PostgreSQL and PostGIS that are a perfect match to use in normal situations, but at this time, we shouldn't create a table for each JS vector file, which we normally do for other projects. Also, the count of files is more than we usually worked on. Then an idea came to our minds to use JSON columns for attribute data and use PostgreSQL as a NoSQL database. And for the geometries, use geometry column for every type of geometries. At our first proof of concept, we create the following table. As it is seen, it's a simple table with 4 columns. It has 2 integer columns for ID, layer ID, 1 JSON column for attributes, and 1 geometry column for geom. At our first approach, we convert shape files to GeoJSON files via OGR2s and iterate through to store in the created table for each feature as a row. Properties of GeoJSON is stored in JSON column, and we gave each shapefile an ID to differentiate each vector file in the table as a layer ID. We stored 10 or more different shapefiles in the same table for the tests, and bam, it's working. We proved the idea, but that's not enough because, as it is stated before, each shapefile can be changed in the period of the project, and our customer wanted to see previous versions of the files and check for the changes. So, we have to add a version system to our newborn idea. First, we start creating a new table to store older versions with almost the same structure as the previous table. Also, we have to change the previous table as follows. As it is seen in the table, we added version as an integer to store the version number of each record. Also, the version table has 2 additional columns. One is record ID to reference rows in the record table. The other one is diff.json column as a JSON column to store differences for query or log purposes. Then we create a trigger function to check for changes on records for updates and delete operations. Each time, this function checks for the differences with the help of PostgreSQL JSON functions in attribute column and stores them as differences in the diff.json column. Also, we have done some optimizations to database, such as converting JSON columns to JSONB for query and performance issues. After several tests, this structure also worked as it is planned. Now we are storing multiple files in the same table with version history. We are happy to finish the tasks, but it hasn't finished yet because when shapefiles are uploaded, the attribute names are shown as it is in the shapefile, and our customers wants to show them with their aliases. It starts with this idea and ends with the following. As you can see here, we created several options for each attribute field for each layer. For example, in JSON defined on the left, there is an enum layer ID definition, which links these two layers on the selected field, enum match field. With the help of this, users define the county ID for a layer and get county name from the county data, which is also stored in the same table as a different shapefile. Also, there is a normal enum ID definition on the right, which matches the domain structure defined in the application. The JSON shown here is the output of the web application to define how to show vector data on the application. There are some other options to show fields just on the attribute table without showing them in the pop-up on the map, or data will be aggregated to show their sum, average, or with custom function in their attribute table. In addition to this, we also use following PostgreSQL and PostGIS features in our application. Export data as GeoJSON with the help of JSON functions directly from SQL. Export data as KML with or without symbology directly from SQL. Getting recursive data from file, folder, structure tables. As a result of all these features, there is no need for extra manipulation at the middleware, which both accelerates the development process. With all these features, PostGIS is absolutely a JS developer-friendly tool to use in your projects. To this point, we show how to use vector data in our application, but our customer also need extra things to finish the project, because there is also digital elevation model data to query and draw profiles from this DAM data. Also, we added DAM data to PostGIS and query multiple points to generate a height profile in fancy charts. Do you think the story is over? Of course not. Our customer is working on the field, so they are collecting time series data on the field and want us to show them in the application, both on the chart and the map. We also use PostgreSQL to show this time series data. There can be queries resulting in 250,000 data points handled by the PostgreSQL. At the moment, our customer is storing 956 different shapefiles with their versions and 14,200 other file types like documents, XLS, PDF, and JPEG, and 1.8 million rows of time series data on their PostgreSQL database. When we check the database and system metrics in general, there are total tables is 16, total database size is 13.2 gigabytes, total vector table size is 4.5 gigabytes, and raster table size is 8.5 gigabytes. And when we count the rows of the single vector table, there are at the moment 2.3 million rows. Total system size is 248 gigabytes with all the files. As it is seen here, PostGIS and PostgreSQL handle the most important problems we have faced in this journey. But also we want to talk about other components of the application to show how open source technologies serve better when they are together. By the way, there are only 16 tables in PostgreSQL to manage this kind of application, which help us to accelerate the development process. In our application, we also use GeoServer, Node.js, GDAL OGR, and OpenLayers to make perfect combination of web technologies. GeoServer is used for serving raster data and publishing some layers in OGC standards like VMS and VFS. With the help of views or materialized view in PostgreSQL, some of the data in the vector table, the single table, can be published as VMS or VFS to share information with the other applications of the customer. Node.js is used for middleware purposes to query layers, manage users and authentication, and etc. GDAL OGR is used for conversion of shapefiles, even in other projections rather than EPSG 4326, and OpenLayers is used for showing the results of all the things we mentioned. At every project we have done, we focus on user experience before other things. UX is the final point every customer faces at the end of the project. If your UX fails, your customer won't select you next time or advertise you to others. It doesn't matter how your backend is perfect, speedy, or doing things at the same time. So we want to create a perfect user experience with a perfect backend that I mentioned earlier. We believe in Pareto principle, or known as 80/20 rule, in our projects, which is 80% of time you are using the 20% of the features of the application. So we write down all the features at the beginning of the project and decide with the customer to focus on most important ones. By doing this, we focus on the most important features to make them better, quicker, and user-friendly. Our customer wanted to copy features of a desktop.js applications to this web.js application, and we write down all the features of desktop.js applications and selected the most used ones in 80% of time. As a result, the following list is created. Basic mapping features like zoom in and out, measure distance, area, drawing features, add base maps, load, view, and manipulate data, change symbology of data, export full or part of the data as an Excel, KML, or shapefiles, print the map on the screen as a PDF or PNG, link non-JS data to JS data like photos, PDFs, query and basic analysis of data, share data with others. After talking about general philosophy, let's talk about the final application created. As it is seen from the screenshot, we created a ribbon menu for the project because almost everybody is using Office applications such as Word, Excel, or PowerPoint. We have been working on this UI for more than 6 years, and our previous customers also liked it. So this was also the same for this project, and our customer liked it very much. The structure is also very similar to desktop.js applications, like there is a layer file tree on the left part and information bar at the bottom. In the middle, there is a huge map area to show various JS data. On the next slide, you will see the upload file window. There are 3 types of upload options. One is generic files such as Word, Excel, PDF, or photos. Other one is spatial files. These are shape files or geotiff files. And the third one is time series data from an Excel template. Uploaded files attribute table is also seen below. And there is also related files photos window, which will be shown when there is a relation between spatial data with files and folders. As I mentioned before, the system is just working like a file system. At the top of the hierarchy, there are projects. The folders are below the projects, and all types of files are uploaded under these folders, so you can easily manage your file and folder structure. Folder and file details are seen in this slide. When you right-click on the file or click on the gear icon, you will access related menus according to file type. For example, if you select a file that is a spatial type, Then you will see Zoom to Layer or Download KML menus. When you view all files, the same hierarchy will be found on the left side of the panel. On the right side, you will see different menus like versions of file and share file. When you view the details of versions, you will see what's changed, when and who changed. When you click on share file, the system automatically creates a link for a selected time period to share data with others. In this slide, you will see select by location analysis and its results. We store all vector data in the same table in PostGIS, so this kind of analysis will be quite easy and performant. Cartography is a very important issue when it comes to GIS data, and our system gives different cartography options to users without knowing the GIS tools. Both raster and vector symbology management can be done from here. There are three types of symbology. One is single symbology for point, line string, and polygons. One is categorized symbology, which are also for point, line string, and polygons. Categorization is done according to selected attributes. And the final one is raster symbology. They are stretched, classified, and unique values. As it stated before, time series data also stored in PostgreSQL, and the query results of time series can be both seen on the fancy graphs and maps as a bar graphs. The final tool in the system is the profile tool, which queries multiple points on the DAM data with the help of PostGIS and shows the result as a smooth graphical representation. You can also export the data beneath the profile. And what's next? As we get feedback from the customers of this application, we will create a roadmap for us. The next steps are as follows. Create an Excel add-on to access the maps within Excel. Excel is one of the most popular applications used by more than 750 million people. Storing Excel data like vector data to view and edit easily. Adding offline support via progressive web apps. Adding statistical module to create average of or sum of attribute values and also the histogram. Adding a workspace feature to save current opened layers, tables, and other configurations. Adding commands to data rows. And the final one is adding a 3D module via Cesium. As a result of our expertise on this and previous projects, we will definitely choose PostgreSQL and PostGIS if there isn't any pressure from the customer to choose an alternative. PostgreSQL is a ready-to-use powerful database from your startup to enterprise. PostGIS is also a powerful spatial extension with limitless and up-to-date functions like native vector type support. JSON and JSONB types give more flexibility to use PostgreSQL as a NoSQL database, like in our example. Both tools accelerate the development progress and give you more time to create mind-blowing applications. Thanks for listening. Please let me know if you have any questions from the email or social media addresses below. Happy PostGIS Day. Bye.
All right. So that was Alpash's talk. He's also in the session for Q&A if you want to ask any questions in Q&A as well.
Hi, everyone.
Hey. Oh, that's Alpash. Sorry, I forgot. It's been a long day.
Yeah.
All right, let's see if we have any questions. Jessica says, great info, thanks. I thought it was really interesting how, again, in the same way that Sean talked about, like Postgres with PostGIS together met all your needs. There was no reason to bring in any other data store to get what you did, what you needed in terms of functionality. Did you Did you know about the JSON-B stuff before you started this project, or did you learn it as you were going along?
Especially, we have a little information about JSON and JSON-B, but we haven't any case to use it. This project forced us to use JSON-B because there are lots of shapefiles, and we have to find a way to store all different shapefiles in one storage. So all this lead us to JSON.
Yeah, I mean, that's what I've often heard from other people who use JSON-B. I know a lot of database people say, no, you should make a good schema and you should break apart the JSON and do stuff. But I often say sometimes developers don't have control over the data they get, right? And so they don't know what's coming. So they just need some place to put the data. And that's kind of, it seems like that's kind of how you used it as well. Yeah.
Yeah, especially there are also views or materialized views. If there is a need for example, we used GeoServer to publish our some tables as a VMS and VFS, and we create some views and some materialized views if there is a performance need. And we also create some triggers and some stuff to make them automized. So they are all updating, and users in the end see the updated and final version of the data. Also, there is a version thing here, I think. Before the presentations before, there's always people wondering about the versioning. We have also done here with full versioning. Maybe the next step we will add going back to a specific version. At that time, there is no feature, but with our tables and structure, you can easily write some functions or things, and you can easily get go back to specific versions without need anything. With just PostGIS and
yeah, you could actually display the older version. If you say which version do you want, you do that, and then you just spit that back out to a map or something like that. Yeah.
Yes, absolutely.
Yeah, that's nice. So you said this was used for a nuclear power plant, is that right?
Yes.
Okay, so did they give you much pushback about using open source?
Yeah, especially at the beginning, when they search for WebJS in the Google, they directly see some ESRI stuff. So at the beginning, they forced us to use Esri stuff. But with the help of the open source and our first POC, we convinced them to use PostgreSQL and PostGIS, and in the end, they really liked the project. And in features, in performance, and I think if we can start with other things like ESRI or Oracle stuff, I think we didn't push our limits like this one.
Right.
Because I think some people think that there is no technical support or something like that, but I'm thinking on the contrary, because with the GitHub or some user leads and some other things, you are limitless. You can even ask the people directly writing that module. You don't have this option in commercial products. You have to deal with lots of things to ask some specific questions.
Yeah. Okay. Well, any other questions for Alpash? I think that covers it. Okay, thanks again, Alpash. Okay. And Alpash should also get a medal. What time is it in Turkey right now?
It's 23:41.
Yeah, so it's almost midnight for Alpash. So he gets a medal for person staying up the latest for a presentation.
Yes. We slept our children and ready for the presentation.
Exactly. Welcome to giving conferences with COVID. Okay.
Thank you.
Thanks, Alpash.